Linear regression in SPSS is a statistical method that can be used when the dependent variable or the outcome is continuous, and when there is an independent variable or a predictor. When there is only one predictor, then simple linear regression is performed. However, if there are two or more predictors, then multiple linear regression is used. Simple linear regression in SPSS is one of the statistical method that can be performed when there are two variables. One of the variable is an outcome or an exposure or a dependent variable, and another variable which is a predictor, and also can be called explanatory variable or independent variable or an exposure. And when there are two variables, one is outcome and one is predictor, then linear regression can be performed. The predictor can be a continuous variable in which the data are continuous, such as height and weight, or it can be a binary predictor in which there are two levels or two categories within the variable, such as life, death, yes, no, male, females. And the predictor also can be categorical predictor when there are at least three levels, such as occupations, including doctor, dentist, pharmacist. So there have to be at least three levels in the predictor. Simple linear regression in SPSS is a statistical method to examine a relationship between two variables and to try to make a regression model and use it for prediction. Here in this SPSS data view, I had inserted two variables. The first one is the age, which is a continuous variable, and the second one is a systolic blood pressure. Again, it is a continuous variable. To try to find out whether there is a relationship between the age and the systolic blood pressure. The systolic blood pressure here is an outcome or a response or is a dependent variable, and the age is the predictor or the independent variable or the exposure. And we could use the simple linear regression and fit a regression line into the model and determine the relationship between the two variables. Here in this video, I will not explain the assumptions required for performing simple linear regression, and I will leave it for another video, but will show you how to do the regression analysis when there is only one predictor or one independent variable, in this case the age. To do simple linear regression analysis, click on Analyze, scroll down to Regression, and then select Linear Regression. In the new window here, move the systolic blood pressure, as the systolic blood pressure is the outcome, and the predictor into the independent variable. Click on the statistics option here, tick on R squared, descriptive, part and partial, collinearity, confidence intervals. Click on continue, click on plots, and in the plot select the standardized residuals and move it to the y-axis, and the standardized predictor and move it to the x-axis, and take on the histogram here in this box and take on normal probability plot. Click on continue, click on options, no changes, just click on continue, then click on OK. An output is generated for the analysis of simple linear regression, showing here the first table, descriptive statistics, the mean and the standard deviation for both variables, the systolic blood pressure, which is the outcome, and the age, which is the predictor. The second table shows the correlation between systolic blood pressure and the age, and as shown here, the correlation or the correlation coefficient, or the R, is equal to 0.728, and this is a high positive correlation between the two variables, and it is also significant as shown here. In the table here, model summary, the R is given, which is exactly the coefficient of correlation, which is given here, and the R square is just square of the coefficient R. 53% of the variances can be explained by the predictor. So 53% of the variances within the outcome can be explained by the age. The ANOVA table will test whether the slope is equal to 0 or not. A p-value is less than 0.05, so there is a significant, so the slope is not equal to 0. Next table, which is the coefficient table, figure here, which is 1.1, is the slope for the regression line, and the intercept equal to 86.2, and there is a statistically significance value, this one. The next graph shows the regression standardized residual is normally distributed with a fitting curve to it, and again also a PP plot for regression standardized residual is generated, and as shown here, these small circles or dots should be aligned along the diagonal line. Final graph is the scatter plot for regression standardized residual and regression standardized predicted value, and the value need to be between -3 and +3. Simple linear regression with a binary predictor in SPSS. Linear regression is one of the statistical analyses that aims to find out if there is a relationship between two variables. One of the variable is an outcome or a response or a dependent variable, and the other variable is the predictor or the exposure, or it is the independent variable or an explanatory variable. And when the predictor have two levels in it, such as life, dead, male, females, then it is called binary predictor or dichotomous predictor. Here I have two variables. The first one, which is the sex, which has two levels in it, 0 and 1. And if we click on the variable view, the values for 0 represent females and 1 males. So the 6 variables is binary variables or dichotomous variable as it has two levels in it or two categories. The systolic blood pressure is a continuous variables and it is the outcome. And to find out whether there is a difference in the systolic blood pressure between males and females, and whether the systolic blood pressure is higher or lower in males compared to females, then the simple linear regression analysis will be performed. Let's look at the descriptive stat for these two variables by clicking on analyze, then scroll down to descriptive statistics and then select explore. Reset this and move the systolic blood pressure into the dependent list and the 6 into the factor list. And in the statistics icon, click on the descriptive as shown here, click on continue in the plot, untick the stem, tick the histogram, tick normality plot test with test, click on continue. On options, no changes, and then click on OK. A descriptive tables are generated as shown here. The 6, there are 2 genders in the variable 6, female and male. There are 50 individuals in each group. And if we look at the second table, it's clearly shown here that the females mean is 135.7 and the male means is 147.6. So the systolic blood pressure, the mean for systolic blood pressure for the females is lower than the systolic blood pressure for the males. And the difference between these 2 means will be 11.9. So there is a difference, and the males have a higher systolic blood pressure. However, in this explanation, I will not discuss or describe the assumptions for performing simple linear regression, and that will be left for another video. To do simple linear analysis with a binary predictor, click on analyze, scroll down to regression, then select linear. In the new window here, move the 6 to the independent variable and the systolic blood pressure into the dependent variable. And on the statistics icon, tick for R-squared change, descriptive, part and partial correlation, collinearity, diagnostic and case-wise diagnostic. Click on continue. In the icon for plot, tick on it and then select and drag the standardized predictor and move it to the x-axis and the standardized residual into the y-axis. Tick on the histogram here, tick on the normality or normal probability plot, click on continue. In the save icon, no selection for any of the options here, click on continue. For options, no changes, and then click on OK. An output is generated with several tables and diagrams. As shown in the first table here, the average mean for systolic blood pressure in general is 141.7. Now, as shown previously that there is a difference in the mean between males and females, the second table here shows the correlation between systolic blood pressure and 6. And as shown here, the correlation is coefficient, which is R, is 0.31. The p-value is less than 0.05, so there is a correlation and significant correlation between systolic blood pressure and 6. If we move to the table, which is the model of summary, shows that the R is 0.31, which is the Pearson correlation coefficient, and the R square is the square of the R, though the value here is very low, which is nearly 0.1. What does this R squares mean? It means that 10% of the variation in the outcome can be explained by the 6. Moving to the next table, which is ANOVA, shows that there is a significant value, p-value, as it is less than 0.05. So the model has been generated and it is tested that the coefficient are not equal to 0. So there is a relationship between sex and systolic blood pressure. The next table shows the coefficient. The constant here is the intercept, which is 135.7, and the sex is 11.9. And that value here, or this value here, represent the systolic blood pressure mean difference between males and females. And as we have seen that the mean for systolic blood pressure for males are higher than females, and there is a significant difference here. The next graph here shows the regression standardized residuals, and shows that the dependent variable systolic blood pressure, the distribution with the mean. The next shows the PP plot, normal PP plot for standardized residuals as shown here. The circles or the dots should be aligned along the diagonal line. Linear regression with categorical predictor in SPSS through generating a dummy variables. Linear regression is one of the statistical method that is performed to find out whether there is a relationship between two variables. One of the variables is the outcome, or the dependent variable, or the response variable, and the other variable is the predictor, or the exposure, or the independent variable. To perform linear regression, the outcome variable have to be, or has to be, continuous, and the predictor variable can be a continuous variable, or can be a binary variable, or a categorical variable. Linear regression analysis in SPSS can be performed with binary predictor, with continuous predictor, but for categorical predictor there is no direct options. It has to be done through generating or recording the variable into a dummy variable. Here in this data view I have two variables: systolic blood pressure, which is continuous variable and it is the outcome, and the age, which is the predictor and it is categorical. There are three categories in the age variable as shown here, and they are given a value of 0, 1 and 2. And if we click on the variable view and then look for the age variable and click on the values, 0 value is given to an age group or category from 18 years to 45, and the 1 value for the age group from 46 to 70 years old, and a value of 2 for a age group of greater than 70. So to find out whether there is a relationship between those two variables, so the age variable here is the predictor and it is categorical and it has 3 levels in it. Let's first of all look at the descriptive data for the variables. If we click on analyze, scroll down to descriptive statistics, then click on explore, and in the explore window move the systolic blood pressure into the dependent variable or list and the age into the factor list as it is categorical, and click on OK. A table is generated showing that there are 3 categories in the age variable and there are 30 cases in each level. The second table shows the mean for the systolic blood pressure for the age group which is the youngest group from 18 to 45, and it has a value of 116.3. For the second group or level in the categorical age variable, the mean is 155.7, and for the third level in the variable, the mean is 189.6. There is a increase in the systolic blood pressure with the age group as shown here. To do linear regression in SPSS for a predictor that is categorical, there is no direct options to select. We need to transform the predictor variables into a dummy variables, and the way to do that is to click on transform and then scroll down to recode into different variable. And so we are going to generate here 3 different dummy variables for the age predictor. So in this window, select the age, drag it into this box, and then give the output name for the variable, such as cat1 for category 1, which is the youngest one, and in cat1 it's going to be between 2 brackets from 18 years old to 45 years old. Close the bracket and click on change, and then click on old and new. So we're going to record the value for the first category in this age variable. For the first level in the age variable, the old value or the first value is 0, and we're going to change that into 1, and then click on add, and anything else in the that dummy variable will be equal to 0. So if we click on all other values equal to 0, add that, and then click on continue. So what have we done here? The first dummy variable is generated, which is called cat1, and every group that is between the age of 18 to 45 is given a value of 1, and the rest are given a value of 0. To do the second dummy variable, click on transform, record into different variables. Now we're going to change the output into cat2, and the cat2 is going to be assigned for the age between 46 to 70 years old. And if you click on 70, enter 70, click on change, and then click on old and new values. Here we're going to first of all cancel all these, remove them, and remove the second one. And for the second level, which has a value as shown here of 1, so the old value is 1 for the level 2, and we're going to keep it as 1, and then anything else will be 0. Add 0 here, and then add the new values. Click on continue and click on OK. A second dummy variable is generated for the second level, and the second level, which is from age 46 to 70 years old, is given a value of 1, and the rest is given a value of 0. And finally, doing generating the dummy variable for the third level or the third category, which is greater than 70 years old. Insert the first of all is category 3, and then insert greater than 70. Change the output variable into cat3, and then click on change, and then click on all the new values. So the old values for this level was 2, and it's going to be, first of all, we need to remove these old values here, and then in the old value here, it was 2, change that into 1 and then add that, and anything else will be given a value of 0. Click on add and then click on continue and then click on OK. A third dummy variable is generated with the third group, which is greater than 70, is assigned a value of 1 and the rest are assigned a value of 0. So this is the way to generate dummy variables in SPSS with categorical variable that have 3 levels in it. To do linear regression, click on analyze, then scroll down to regression and then click on linear. In the linear regression window, select the systolic blood pressure and move it to the dependent box or variable. And in the independent variable, which is the predictor, the way in SPSS it works is that 2 dummy variables are inserted here and the third will be left out as a reference. So here we're going to leave the youngest category, which is 18 to 45 years old, as a reference category to compare to, and just select the cat 2 and cat 3 and move them to the independent box here. Click on OK. An output is generated here. A model summary is generated showing the R, and it is very high, and R square is 93.7%. So 93.7% of the variation in the systolic blood pressure can be explained by the age predictor. What is important in this output is this coefficient table, which shows here the category 2 and category 3, and category 1 is not shown, as category 1 is the reference category. So here the value is for category 2, the coefficient, unstandardized coefficient is equal to 39.4. So this value means that age group from 46 to 70 years old have a 39.4 systolic blood pressure, higher than the young category, which is category 1. And for category 3, the systolic blood pressure is 73.2, higher in this group compared to the reference group, which is the young group from 18 to 45 years old. These values here are significant, as the p-value is less than 0.05. So we have compared here the level 3 to level 1 and level 2 to level 1. What if we want to compare cat 3 to cat 2? Go back again to the linear regression, and now we're going to leave one of these dummy variable out and inserting cat 1 in the box here and cat 3, and then using the cat 2 as a reference category to refer to. And if we click on OK, again scroll down here, we get a new table with coefficient. Now here the reference group or level is category 2, and it's missing here. So cat 1, when it is compared to cat 2, it is in minus, because cat 2 have a higher mean than cat 1. So the systolic blood pressure is 39.4 lower than cat 2, and comparing category 3 to category 2, there is a 33.8 higher blood pressures, and here it's also shown that this is significant. Multiple linear regression in SPSS is a statistical method that can be performed when there is an outcome that is continuous, and this outcome can sometimes be called a response variable or a dependent variable, and at least two or more independent variables, or they are called exposure or predictors or explanatory variables. So the test can be performed when there is an outcome and at least two or more predictors. And the objective of the multiple linear regression to examine and assess the contribution of the predictors to the variation in the outcome, or in another way, how well the predictors explain the variation in the outcome. Here in this SPSS data view, I have three variables: systolic blood pressure, which is a continuous variable and it is the outcome, and an age and weight predictors, which are an explanatory or an independent variable. So age and weight are independent variables and the systolic blood pressure is the dependent variable. To examine whether these two predictors can predict or contribute or can explain the variation of the systolic blood pressure, then multiple linear regression will be used and not simple linear regression, as simple linear regression can be performed when there is only one predictor. In this video, I will not go through the assumptions for performing linear regression, multiple linear regression, and this will be published in a separate video clip. To do multiple linear regression, click on Analyze, scroll down to Regression, then select Linear Regression. In the new window, move the systolic blood pressure to the dependent variable, which is an outcome, and then select the age and the weight and move them into the independent box or independent variables. Click on Statistics and then tick on R squared change, tick on Descriptive, tick on part and partial correlation, tick on collinearity diagnostic, and then tick on case wise diagnostic. Click on Continue, click on Plots. In the Plots window, select the standardized predictor and move it to the x-axis, and the standardized residual and move it to the y-axis. Tick on histogram and tick on normal probability plot. Click on Continue, tick on Save, and in the Save, tick on the Cook's distance, and then click on Continue. In the options, no changes will be performed. In the styles, no changes. Click on OK. Several tables and figures are generated in the SPSS output, and the first table is a descriptive statistics that shows the mean for systolic blood pressure, age, and the weight for the two predictors and the outcome, with standard deviation for each. The second table is the correlation table, which shows the Pearson correlation between systolic blood pressure, age, and weight. To perform multiple linear regression, one of the essential criteria or assumptions that there should be a relationship or correlation between the outcome and the predictor. Here it shows that the age is correlated with systolic blood pressure and the value for correlation coefficient is 0.72, and the weight also correlate with systolic blood pressure, which is 0.53. So there is a correlation between the outcome and the predictor. Another assumptions that have to be fulfilled to perform the multiple linear regression, that there should not be a collinearity between the predictors. So the age and the weight should not correlate with each other, and the way to check that is to look at the correlation between age and weight, and the value is less than 0.7. As far as the correlation coefficient is less than 0.7, then there is no multicollinearity, and here the value is 0.4. So this one of the assumption has been fulfilled. So this table shows that there is a correlation between systolic blood pressure, age, and weight, and the value to consider that there is a correlation is to be greater than 0.3. And there is no multicollinearity between the predictors, which is age and weight. Moving to the table, which is the model summary, it shows an R and an R square and adjusted R square. I will analyze the R square. The R square here shows that 59.3% of the variation in the systolic blood pressure can be explained by age and weight, which is the predictors, and this value is significant. Moving to the next table, which is ANOVA, that tests whether the slope is equal to 0 or not, and the ANOVA shows that there is a significant p-value is less than 0.05. Moving to the coefficient table, it shows here the unstandardized coefficient, or the beta, for the age and the weight, and we will use the standardized coefficient beta as both age and weight are measured at different scale. Age is measured in years and weight is measured in kilogram. So we only be able to analyze the standardized coefficient for beta here. So this value here shows that age is 0.612. What does this value means? It means that for every increase in 1 year of age, there is a 0.61 increase in the systolic blood pressure, and this relationship is significant as the p-value is less than 0.05. For the weight predictor, for every increase of 1 kilogram in the weight, there is an increase of 0.27 in the blood pressure, and this value is significant. So both predictors contribute to the explanation of the variation in the systolic blood pressure. Moving to the residual statistic table, again, this is a table that is important for multiple regression analysis. Looking at the standardized residual, the value should be between -3 and 3, and the Cook's distance is between 0 and 0.137. As far as the value is not greater than equal to or greater than 1, then this is fine. Moving to the next plot, which shows the standardized residual, and it shows that the systolic blood pressure is normally distributed. And to looking at the next plot, which is the PP plot, standardized residual, shows that the residuals should be, which is the blue circle, should be aligned along the diagonal line. And finally, scatter plot showing the standardized predictor on the x-axis and standardized residual on the y-axis. and the dot should be between -3 and +3 for both the x-axis and the y-axis.